So for this video we have to take a little bit of a detour in our reactivity and redox work to the rusting section of the IGCSE syllabus, because it is a redox reaction. It is a metal reacting with oxygen, but there are very specific things they expect you to know about rusting that we need to make sure are clear. So rusting, the conditions for rusting are often shown through this experiment. So to get rusting, you obviously need some iron, you need oxygen, and you need water. Without water, the process is effectively stopped. It's too slow for you to sit on a timescale. Water almost speeds the whole reaction up. Also, if you have salt in the water, if you live near the sea, as we do here, it speeds it up even further. But the three main conditions are iron, oxygen, and water. As you can see, in a boiled water, which contains no oxygen, you would get no rusting because we are missing one of the components. We have the iron and the water. In a system where you have calcium chloride to keep the air dry, so that there is no water in there, so you only have the iron and the oxygen, you would get no rusting. It would be way too slow. But if you have air and water and iron, you are going to get rusting. So in this case, tube C would show rusting over time. So all three components are needed to get rusting to occur. So just to check that we are clear what we mean by rusting. Rusting is the formation of iron oxide. So you would take iron, you would take oxygen, and in general, rust is iron in its 3+ oxidation state, so Fe2O3. Rather than, as you do know, iron can be 2+. It tends not to be that way when we do rusting. It tends to oxidize all the way to the 3+, lose as many electrons as it possibly can, and end up in this situation. And obviously this would need balancing. So we would have to have a 2, a 3, and a 2 there. We would need 2 ions. 4 ions to make the 4 ions there, and 3 O2s to make your 6 oxygens over here. Now we could write this as half equations if we wanted to. It would be good practice because obviously we know we've got iron 3+ over here, as I've said, and it's had oxygen added to it, so it's been oxidized, and we know oxygen is going to be O2-. So you could, if you wanted to, write half equations for this, making sure that you use all the balancing throughout. I will leave that for you guys to do, and I'll jump back at the end to show it so you can have a pause and have a go at it. So hopefully you paused, had a go at the half equations. If not, they're now written out. So you would take 4 ions, you would end up with 4 3+ ions and 12 electrons. 4 times 3, 12 electrons have been lost, and obviously they're after the arrow because they have been lost. Then 3 O2s plus the 12 electrons would make your 6 O2- to balance those out. So how do we prevent rusting? And this is the main bit they tend to ask you about. A few different ways. There are barrier methods. This is literally coating the iron in something so that the oxygen molecules can't get in and the water can't really get in. So things like painting, coating in plastic, oiling, placing a layer of oil over things, are all barrier methods that will stop the oxygen being able to get to the iron to react with them. Because what is happening when we have rusting is oxygen is colliding and taking the electrons off of the iron, as we've seen here. So any kind of barrier that stops the oxygen ever getting anywhere near the iron, those electrons can't move, you don't get rusting. Barrier methods are cheap, so these tend to be very, very cheap. But as soon as you scratch them, any kind of scratches or dents in them, etc., means they don't work anymore. As soon as there's a scratch through and you can see the iron or the oil gets rubbed off, the oxygen can get through and you will start to get rusting. So they're more temporary. You would have to keep renewing the layer of paint to avoid any scratches to stop the rusting happening underneath. A slightly better method is called galvanizing. So galvanizing, you would layer some metal over the top, preferably something like zinc. So as you can see from this diagram, you would put a layer of metal over the iron, a more reactive metal than the iron is usually used, usually zinc or something similar. Because first of all, it would act as a barrier initially, so same as the barrier methods, you would stop any oxygen or water getting in there. However, when you scratch a galvanized layer and the iron is exposed to the oxygen, it will still protect the iron from rusting. And this is because the zinc is more reactive than the iron. It's higher up our reactivity series. It wants to be oxidized more than iron does. So when the oxygen collides with the iron, obviously the oxygen will react with the iron, take away the electrons, but the zinc will then give the iron electrons. It will reduce the iron back to pure metal, and the zinc will become oxidized and break away instead. So galvanizing protects as a barrier initially, but any small scratch continues to protect afterwards. So to show what I mean by that protection afterwards, we'll go on to the final kind of sacrificial protection, which works in a very, very similar way to galvanizing, except you are not creating the barrier method in the first place. Now, coating something entirely in zinc, particularly if you're talking about a ship, is incredibly expensive. But as we said, once the zinc's scratched, you have this kind of sacrificial reaction where the zinc will react with the iron to keep it as iron metal. So you can, instead of coating the whole piece of iron in it, just attach some zinc or magnesium or something that is higher up the reactivity series than iron is more likely to be oxidized than iron is, and get that to protect your iron. So the zinc will happily go from zinc to zinc 2+ and give out electrons. And because it will do that more readily than iron will, if there is any iron around that is already oxidized, that is already reacted, it can gain those electrons and turn back into pure iron. So sacrificial protection is a redox reaction. The zinc is being oxidized to help reduce the iron back into pure iron rather than the rust, the iron oxide that it's become from the reaction. Now, one big problem with sacrificial protection is obviously eventually, and with galvanizing, I suppose, eventually all of that zinc, all of that protective metal is going to be reacted away. It's all going to have turned to zinc 2+. So you have to replace these sacrificial parts over time so that your iron never ends up rusting. There has to always be more pure zinc there to do the oxidation reaction to be able to reduce the iron back to its pure metal and prevent the rusting. So you need to make sure that you understand what's going on in each of these three cases, and why sacrificial protection is a redox reaction and how the zinc tends to react within that.